So we're going to now talk about the final step of the translation to SSA, which is versioning variables. So in this step, we are going to rename the mentions of a variable. We have already added the trivial 5 functions, and we are going to now rename the mentions of a variable such that the program now becomes in SSA form, which means that every assignment to a variable version is happening at most once in the static text of the program. And for this, we process all the user definitions, for example, A equals B plus C, and all the 5 functions that have been inserted by our algorithm in step 2 in the same traversal. And the idea is very simple. We are going to do a depth-first search traversal of the CFG, and at each step of this depth-first search traversal, we are going to keep track of the current version of the variable. And depending on the current version of the variable, if that variable is being used in the current node of the DFS traversal, then we are going to rename that node with the current version. If that variable is being assigned, then we are going to increment the version and then give that assignment variable a new version. And this happens, this is done for the DFS traversal basically visits every node at most once. So to do this, there's a visited set that's kept, and you basically ensure that every node is visited at most once. Okay, so this is our pseudocode for the DFS traversal. It's pretty much the standard depth-first search traversal with a slight twist because of the 5 nodes. I want to talk about that very quick soon. So we initialize the version map, which is the version map for every variable. And this initialization basically gives 0 version for every variable in the program. Right? So basically initially every variable is basically given the 0 version. And then we call the depth-first search procedure, which I'm going the recursive depth-first search procedure, which I'm going to call DFS, into on the entry node of the control flow graph. And with this VMAP, which is initial VMAP, which is initialized with 0 version for all the variables. Now, for given n, a node n in the graph and a VMAP, the DFS function renames n's variables. So within n, the node n, so n represents a node in the control flow graph, which means it represents a basic block in the control flow graph. And inside that basic block, there will be instructions like A equals B plus C, etc. So for all such instructions, A equals B plus C, rename B and C with their appropriate versions, right? So for those B and C, basically they represent the non-phi uses, and you rename them using VMAP. So for example, it becomes B0 plus C3 or something like that. Similarly, you create a VMAP prime. So if there's an assignment, so when I say uses, I also include assignments. So for example, A equals B plus C, then because A is an assignment or A is being assigned to, then if the current version of A in the VMAP was, let's say 3, then I increment it by 1 to 4 and then make this as A4 equals B something plus C something. So that's what rename n's variable non-phi uses using VMAP means. Then there's one slight twist here. For the 5 nodes at my successors, I'm going to rename the variable corresponding to my branch in that 5 node in this step itself. So when I'm visiting node n, I'm also going to rename, just like I renamed all the non-phi uses in my basic block, I'm going to rename the phi uses in the successor of n. Notice that I'm not renaming the phi uses of n in this step. I'm going to rename the phi uses of the successor of n. And overall, that's going to ensure that all the phi uses are also renamed appropriately. So before I do the renaming of the phi arguments of the successor, I create a VMAP prime by copying VMAP and incrementing the versions of the variables modified by in n. So for example, if A has been modified in n, then the new version of A will be 4 in VMAP prime. And for each successor S of n, if the successor S contains a phi arg or contains a phi node, then one of those arguments of that phi node or phi function will be corresponding to n in that successor. That's what a phi function means, because it will have as many arguments as the number of incoming edges to S. And one of those arguments is going to refer to n, and rename that particular argument, only that particular argument in S based on VMAP prime, because that represents the latest map after all the assignments in n have been completed. And if S has not already been visited, this is the standard visit every node once only in the DFS, called DFS S comma V prime. And this is guaranteed to terminate when order n time. Order n visits of the DFS, because it's basically revisiting each node at most once. When I say order n, I mean order V plus E, where V and E are the number of nodes and edges in the control flow graph. So what is the running time of this algorithm? It's not just okay to just count the number of DFS traversals, but within each DFS traversal, we may be doing a non-constant amount of work, which we are. And so to be able to talk about the running time of this third step of translation to SSA, we count the number of mentions of a variable, and we are going to first count the number of mentions of a variable, where a mention includes both a use or a def of a variable in the original program. So for example, on a node X, on a basic block X, if m orig X represents the number of mentions in the node X, then the total number of mentions in the whole program is basically summation over X, m orig X, where X is a node in the control flow graph, and that basically represents a basic block. When we convert the program to SSA by introducing, let's say, trivial phi nodes, then the number of mentions of a variable in the final program is, for each new assignment a phi x that I add. So the only new assignments that I add to the program are all the phi functions that I've added. So for each such assignment, the number of mentions is basically m phi x is increased in the new program, the final program, by the in degree of x. Because if the new mention is something like a equals phi of a1, a2, phi a dot a, then the number of mentions that are present in this single instruction is basically proportional to the in degree, or the number of incoming incident edges at this node. So the number of, for each assignment of this type, the amount by which number of mentions increases because of the phi node is basically given by in degree of x, and so we say m phi x plus equals in degree of x, and the total number of mentions in the new program, in the program in which the trivial phi nodes have been inserted, is mx final equals mx orig plus mx phi, where mx phi represents all the mentions due to the newly added phi nodes in step 2. Now, here's the interesting thing. How many different new assignments could have been added because of this step 2? Well, it turns out that there can be up to order n square new assignments, where n is equal to the number of assignments in the original program. And this is because the number of different variables that need to be versioned using the phi node may be up to order n in every basic block. Because for every basic block, there could be up to order n variables that are reaching that basic block. And so because of that, and if all of those variables have different versions reaching through different incoming edges, then for each of those variables, we need to create a different phi node. So for every basic block in the program, I may need to add up to order n phi nodes for each different variable. And the number of basic blocks is also order n. So effectively meaning that I may have to add a total of order n square phi nodes in the overall program. But typically this number is linear, even though it can be worst case order n square or quadratic. Typically this number is linear in n, where n is the number of original program statements or original assignments in the program. Further, because a phi x, the number of new assignments can be order n to order n square. The in degree can be order 1 to order n. So it can be maybe the in degree is at most 2, but in the worst case it can be order n, because maybe a lot of different nodes can potentially reach a particular basic block. And so because of that, the number of mentions is basically obtained by multiplying the number of new assignments by the in degree. And if the number of new assignments can be n to n square, and if the number of in degree can be order 1 to n, then the number of mentions in the new program can be order n to n cube. And so we can have a cubic number of mentions in the final program compared to the number of mentions in the original program. Recall that in the original program, the number of mentions is proportional to the size of the program, because it's a 3 address code representation. So every instruction can have only a constant number of mentions, maybe up to 2 or 3. But because of the SSA transformation, every instruction, the phi instructions or the phi functions can have more than a constant number and up to order n number of mentions. And that is the reason why we can have an order n cube worst case blow up in the number of mentions that we have in the program. But the good news is that typically this blow up doesn't happen, and the typical case is order n only. So the program doesn't grow by a cubic factor but just stays linear. Finally, if I talk about the running time of the step 3 of the translation to SSA, then we need to look at each mention at least once and rename it. So that is basically order of m final, which is the number of mentions in the final program. And so this can, as we have said, m final is between order n, which is the typical case, to order n cube, which is the worst case. Overall, if I look at the overall translation to SSA algorithm, it was divided into 3 parts. The first part was the computation of dominance frontiers, which we said was order E plus V multiplied by the average size of the dominance frontier of a node. And E and V are order n, but dominance frontier could be anywhere between constant size to order n, and so this step can take order n to n square. The second step of the algorithm was placing the 5 nodes, which was basically the time complexity of this was the number of assignments in the final program multiplied by the weighted average of the dominance of the dominance frontiers of all the nodes, where the weighted average depends on the number of assignments in each node. Once again, the number of new assignments that could have been added in the program is between n to n square, and the weighted average size of the dominance frontier is between 1 to n. And so the overall running time of step 2 of this translation to SSA can be from order n to n cube. And finally, the versioning algorithm that does a simple depth first traversal on the graph has a running time complexity of m final, which we have already said is between order n to n cube. Now, and this is a large gap between, I'm saying that the typical case is order n, and the worst case is the order n cube. So I think we need some intuition or some sense of when is it going to be order n and when is it going to be order n cube. And for that, there's this nice theorem that if a program contains only if then else and while do loops, which means while something and then body, then the size of the dominance frontier of any node is always less than equal to 2. And recall that if the dominance frontier, so this can be seen using examples. For example, here E represents a while or an if condition, A represents, let's say, an if condition, and then there's this meet point and so on. And if I look at the size of the dominance frontiers, the superscript basically represents the size of the dominance frontier of each of these nodes. The size of the dominance frontier of E is 0, the size of the dominance frontier of A is 1, and so on. And similarly, here is an example which contains both if then else and while loops. For example, here A represents a while do loop, where the while condition at A determines whether to go to the loop body C or to go to B. And once again, the maximum dominance frontier that you can have here is 2 in this graph, in this example. And once again, here's another example where the maximum dominance frontier you can have is 2. So I'm not going through a proof of this statement that for a program with only if then else and while do loops, the dominance frontier of every node will be less than or equal to 2, but I'm just giving you some examples to kind of introduce the idea. The proof of this is out of scope for our discussion, but if you're interested, you're welcome to look at the original paper, which actually contains the proof. Now, however, so that's a good news, that the dominance frontier will be always less than or equal to 2, which means that the average size of dominance frontier will be always less than or equal to 2, which means that the first step will only take linear time. The second step would also, because of the first step is, the second step is also going to take, roughly linear time and so on. So it's going to be small, but that's not, that's not what really happens in the real world, because in the real world, we don't necessarily have only if then else and while do. We also have repeat until or do while loops. And repeat until and do while loops basically are of this form where, the loop head basically does not have 2 branches, but has only a single branch, but it's the back edge, the node which is actually has an outgoing back edge which has 2 branches, in which case the dominance frontier of a node can be as high as order n, or the number of nodes in the graph. So here's an example. There are these 3 nested loops. The outer nested loop is at loop head A. The second inner nested loop is at loop head B. The third inner nested loop is at loop head C. And in this example, the dominance frontier size of, for example, the node C is 3. In general, for a k-depth loop nest, the dominance frontier size of for some node X can be as high as k, and k in turn can be as high as order n. And so, in general, the program can have order n dominance frontiers. And so, in pathological cases, this algorithm that translates to SSA can become quadratic or worst case cubic. Now you may say, if repeat until and if do while are so bad, then why don't some languages should not just simply not allow these constructs? But that's not a solution at all, because recall that when we do compiler or transformations, then we often convert while do loops to do while loops. For example, recall the loop inversion transformation, or other transformations like loop unrolling or loop splitting. But loop inversion is a primary one. So loop inversion actually completely converts a while do loop to a repeat until loop. And a typical compiler will need to maintain the program in SSA form across these transformations. And so even though the original program may have only while do loops, because of this transformation pipeline, the intermediate programs will have do while loops, in which case it's not guaranteed that the dominance frontier will be less than equal to 2. It can be as bad as order n. So finally, we have the overall running time of the conversion to SSA algorithm is order n typical to order n square worst for the first step, order n typical to order n cube worst for the second step, and order n typical to order n cube worst for the third step. And we have also gotten some sense of when is it going to be good and when it's going to be bad. And notice that these pathological cases where the size of the dominance frontier is very large happens when the loop depth nests are very long or very deep or something like that. And that's not typically the case. And hence, in practice, this is not such a big problem. And that's why the translation to SSA algorithm, the one we have discussed, is often used and typically used in compilers.